In this sample problem, we have a simple harmonic oscillator where at point x equals 0 generates a wave on a rope. The oscillator at a frequency of 40 Hz and with an amplitude of 3 cm. The rope has a linear mass density of 50 grams per meter and is stretched with a tension of 5 newtons. Find the speed of the wave, find the wavelength, write a function of the wave, and find the maximum transverse acceleration of the wave. First we extract the given values from the problem. We have the frequency of the wave which is about 40 Hz, the amplitude of 3 cm, the linear mass density of 50 grams per meter, and the tension on the string which is 5 newtons. To find the speed of the wave of the string, we use equation 1 here and substitute the known values which are the tension and linear mass density of the string. We see that the speed of the wave of the rope is 10 meters per second. To find the wavelength of the simple harmonic motion of the wave we use equation 2. Substituting the known values and the solved speed of the wave earlier we see that the wavelength of the wave is 0.25 meters. To write an expression of the wave function for this type of wave where it is assumed that the oscillator has its maximum upward displacement at time t equals to 0 we simply use the general expression 3. We use this expression since it fits the description given in the problem at time t equals to 0. This would give a maximum displacement when we solve the problem and see its graphical representation on the right. To find the maximum transverse acceleration of a wave we use the wave equation earlier and take the second derivative. First we take the first derivative of the wave function, then take the second derivative as shown here. The maximum transverse acceleration, the sine function, must be equal to 1, so we are left with the amplitude times the square of the angular velocity. Substituting the known values and taking into consideration the equation of the angular velocity we solve that the acceleration is equal to about 1800 meter per second square. This is the value of the maximum transverse acceleration of the wave.